Okay, and we are live. Yeah, let's get started. And here we go. Welcome everyone to my third take of section 5.5, Total Change and the Fundamental Theorem of Calculus. My microphone is yet again doing wild things, and I had my husband take a look at it, and we actually think my computer's audio jack is malfunctioning. So we have switched to the Bluetooth headset for now, and hopefully this will be helpful. Alright, so let's get to it. The fundamental theorem of calculus. So with a name like that, you might think it's probably pretty important to our calculus class. So let's get to it. If f prime of x is continuous for some a less than or equal to x less than or equal to b, then we have the integral from a up to b of this derivative f prime of x with respect to x is equal to the original function, just f, evaluated at the upper bound, f of b, minus the original function evaluated at the lower bound, so f of a. So in words, the definite integral of the derivative of a function gives the total change in the function. So we've kind of been using this just without writing it down fully. Alright, so now we're going to look at example 1, which is how we can use the fundamental theorem of calculus. So we want to calculate this integral using the fundamental theorem of calculus. We could just go ahead and plug this into our calculator and get the answer. However, that's not the exercise specifically asked here in example 1. So let's see what we need to do. We need the integral from 1 up to 5 of 3x squared dx. Okay, by the fundamental theorem, we're told that this must be the original function evaluated at the upper bound minus the original function evaluated at the lower bound. And we were given our original function. Okay, so we can go ahead and plug this in. So f of 5 is going to be 5 cubed plus 2 minus f of 1, which will be 1 cubed plus 2. So 5 cubed plus 2 gives us 127. 1 cubed plus 2 gives us 3, so we have minus 3, and so we get our final answer as 124, which, if you plugged our original integral into your calculator, you could check that this is the correct answer. Alright, so let's move on to example 2, where we have a turkey that is currently at 50 degrees Fahrenheit and is put into an oven at 400 degrees Fahrenheit, and that's happening at time is equal to 0. The temperature of the turkey is then going to rise, and we're given the rate at which it's rising with t in minutes. So the question asks us to estimate the turkey's temperature after 15 minutes. So we know that an integral gives us the total accumulated change, so the total amount of change that happened during a time period. So we're going to need to take that integral over the time period we're interested in, which is starting at t is equal to 0 up to t is equal to 15. Of the rate, we need the integral of the rate, which we were given. It's our 2 times 1.03 raised to the t, and we need to bookend that integral with our respect to t. Okay, and this is going to give us the total amount that the temperature rose during the first 15 minutes. So a calculator will tell us that the temperature increased by 37.75 degrees. Okay, so the turkey started at 50 degrees and then it increased 37.75 degrees. So after 15 minutes, the temperature of the turkey, the temperature of the turkey is this 50 degrees plus the 37.75, which gives us a grand total of 87.75 degrees. And there we have the answer to example 2. Alright, so let's look at example 3. So we're given an unfinished table and we're given the graph of a derivative. So down here this is f prime of x. And we would like to fill out the table of values for the original function f of x. Okay, and we're given that f of 0 is 3. Okay, so that's all we have to go on at the moment. So what we need to do is find out, well, if we're starting at f of x is equal to 3, at x is equal to 0, then we just need to find out how much we need to add or subtract from that to get the next value. All right, so the next value is going to be this f of 2. All right, that's the next value we care about here. So f of 2 is going to be our previous value, which is f of 0, plus the total amount of change, which we know is an integral, the total amount of change that happens in between x is equal to 0 and x is equal to 2. So the total amount of change from 0 to 2 of the derivative. Okay? So we're going to come down here and look at our graph. From 0 to 2, we need to determine how much total change happens here. Well, first of all, we are above the x-axis, so we know we will be positive. All right. And then the next thing we can do is go ahead and use our counting boxes technique. So if you go ahead in here and draw some interesting looking boxes like this, okay, we see that we look like we have one full box here and maybe a half a box and another half of a box over here. So altogether, our total amount of change is positive 2. So f of 0 was the only thing we were given, which is 3. And our total amount of change is 2, means that our f of 2 is 5. And we can go ahead and fill that in on our table. All right, let's do the next one. The next point we're looking for is f of 4. So we know that this is going to be our f of 2 plus the total amount of change from 2 to 4. Okay? Similarly, we could also say that this is f of 0 plus the total amount of change from 0 to 4, f prime. Oh, wild pen. F prime of x dx. Both calculations would give you the same result. I'm just going to go ahead and use a result that from the previous work that we've done to go ahead and just make the computation slightly simpler. Okay, so f of 2 is what we just calculated is 5, and we need to find the total amount of change from 2 to 4. So looking at our graph, from 2 to 4, it looks like we have 4 boxes. Also, we have noticed that each box has an area of 1, so that's why we didn't need to multiply by the area, because the area was 1. All right, so we increased by 4. So f of 4 should be 9. All right, I'm not going to write out the rest of the calculations, but we're just going to kind of look at our graph here and see that from 4 to 5, we're still above the x-axis, even though our line here is decreasing, we're still above the x-axis, so it's still positive. And both pieces of these boxes here and here look like they maybe add up to be one whole box. All right, so we'll have 9 plus 1, which gives us 10. Between 5 and 6, similar situation here. Both pieces look like they add up to be 1, but we are now below the x-axis, so it should be counted as negative. So we have 10 minus 1. We're back to 9 again. 9 again. And then from 6 to 8, we are still below the x-axis. And it looks like we have 1 full box and again 2 half boxes. So 9 minus 2 gives us 7. Okay? And so that is how we can use the counting boxes technique to fill in a table like this when we're only given, remember this was just the derivative function graphed here. Okay, so example 4, a lab is performing tests for a new drug where they're testing how long the drug stays in the body. Let A of x be the amount in milligrams of a drug left in a person's body x minutes after administration. Let lowercase a of x be the derivative of capital A, okay? The rate at which the drug leaves the body. So given all of this information below, all of this information, we're supposed to evaluate A and B. All right, so part A asks us to find capital A of 0. So capital A, remember, is our original function, capital A be the amount, and lowercase a is our derivative of capital A. All right. So we're given a ton of information here. I'm going to go ahead and rewrite the fundamental theorem right in front of us just so we have it. And then I'm going to use the same terminology from this problem. So first I'm going to use bounds from C to D just so we don't get confused with a lowercase a, because then we need our lowercase a of x, which is our derivative, our rate, dx. So our fundamental theorem says this is the original function, capital A, evaluated at the upper bound, minus capital A evaluated at the lower bound. So we need to see if we can use this theorem to find capital A of 0. So if we look closely at both integrals given here, they both have a lower bound of 0, which means if we tried to evaluate them using the fundamental theorem, we would end up looking for A of 0. All right, so let's go ahead and do that. I'm just going to choose the first one, but it would work with either. So we have the integral from 0 to 4 of A of x dx by the fundamental theorem. We have that this is capital A evaluated at 4 minus capital A evaluated at 0. Okay? So then we'll note that we're given capital A of 4. Don't get confused with the lowercase a of 4. All right, so we need capital A of 4. So this is 5 minus A of 0. And we were also given that this integral evaluates to -3. So we can go ahead and switch out the left-hand side for -3. Well, now we can go ahead and solve for a of 0, which is what we wanted to find, right? So if we add 5 to both sides, we'll get 2 is equal to -a of 0. So a of 0 is equal to -2. There we go. Okay. Now for part B, we want to find the integral from 2 to 7 of the lowercase a of x dx. So we're going to use the fundamental theorem again in a similar but different fashion. So we want to find this 2 to 7 a of x dx. Again, by the fundamental theorem, we have a evaluated at the upper bound, which is 7, minus a evaluated at the lower bound, which is 2. If we scroll back up to look at our given information, we are given a of 7, and we are also given a of 2. So we can use these two pieces of information and go ahead and plug them in to our equation here. So a of 7 is 3, and a of 2 is 7. So we get 3 minus 7, which gives us -4, and we've now found the integral. All right? So in both cases, we use the fundamental theorem plus some of the given information. Notice we didn't use all of the given information. All right? So it's important to kind of pick through what is actually useful in a problem when sometimes they give you too much information, right? Okay, and our last example for today is example number 5. So a company finds that the value of their stock is changing at this given rate. Okay, and t is in months. So assuming t equals 0 is January, how is the price of the stock expected to change from March to July? All right, so that's the first part of the problem. So let's go ahead and work on that. So the total amount of change, again, is given by an integral. So we need to find the bounds of our integral. So we are looking for the time period from March to July. So first, let's go ahead and say that March, well, that's the third month. So that means t should be equal to 3. If t equals 0 is January, and t is in months. Okay, and then we have July, so t is 7. So those are our bounds for our integral. We're going to start at 3, go up to 7. We want to take the integral of the rate function that we highlighted. So this is 10 minus 0.05 t squared. Notice I have addition and subtraction here, so I'm going to go ahead and put this all in parentheses so that we know that we're taking the integral of the whole thing, and then just cap it off with our dt. So if we go ahead and plug this into our calculator, we'll find that this is 34.73. So the first thing we notice is that this is positive. So the price of the stock is expected to rise because it's positive, by $34.73 between March and July. Okay? And then the last part of the problem said if the stock price is $102.56 in March, what is it worth in July? Well, so for that we just need to take our 102.56 and add it to our 34.73, and we end up with 137.29, and this is the expected value of the stock in July. Okay? And so with that, we wrap up section 5.5. Please don't forget to take the comprehension quiz, and I will see you in 5.6.